Hello everyone, my name is Gili. I'm a PhD student at the University of North Carolina at Chapel Hill. In this talk, I'm going to present our paper titled Learning in the Wild: When, How, and What to Learn for On-Device Dataset Adaptation. Let me first introduce the problem we try to solve in this paper and its motivation. Nowadays, the most popular way of enabling on-device deep inference on IoT, mobile, and embedded devices is first to train a DNN, deep neural network, offline with the GPUs, and then load the trained model into the target device. And finally, the devices are deployed in the real world where they perform inference tasks based on their trained model. However, there exists a problem called Dataset Shift that degrades the inference accuracy of the intelligent systems deployed in the wild. The Dataset Shift problem happens when the training data distribution and real data distribution become different. So, for example, when the DNN is trained with the Arctic data, it provides high inference accuracy, which is 99% in this example. However, when a dataset shift happens, which changes the Arctic data into desert data, its inference accuracy drops to 32%. This is an important and real problem to be solved, since this learning environment mismatch actually happens to many practical intelligent systems deployed in the wild. Unfortunately, mainstream machine learning methods only work by ignoring the dataset shift problem. An example of dataset shift is a face recognition algorithm trained on young faces. When the dataset has changed to have a much larger proportion of older faces in it, the face recognition system will fail to correctly identify users' faces. To solve this problem on the device, we propose on-device dataset adaptation in this paper. By enabling on-device dataset adaptation, an intelligent system becomes able to provide satisfiable learning performance, which is inference accuracy specifically when the learning environment changes. This example shows the effectiveness of on-device dataset adaptation. When a dataset shift happens, which means that the training data and real data distribution becomes different, the new data is incorrectly classified if the model adaptation is not performed. However, by updating the model's decision boundary through the model adaptation, the new data can be correctly classified. The goal of on-device dataset adaptation is to adapt an intelligent systems to an ever-evolving learning environment when the possibility of dataset shift is allowed. In this paper, our work tries to divide the on-device dataset adaptation problem into three subproblems, which collectively enables an intelligent system to adapt to an ever-evolving learning environment, which actually happens to many practical intelligent IoT systems deployed in the wild. The three subproblems we're trying to attack in this paper are: first, when to perform the on-device adaptation to the environment. Second, how to perform the on-device adaptation using only limited resources of the system. And lastly, what examples to select to learn for efficient and effective on-device adaptation. The first problem is when to learn. In order to determine when to start adaptation, feature distribution of each class generated by the penultimate layer of the model is built with input examples coming to the system. This figure shows an example of feature distribution of 4 classes in two-dimensional space. Based on the feature distribution, the dataset adaptation is initiated when the feature distribution divergence that quantifies the similarity between the source training feature distribution and target real feature distribution becomes larger than the divergence threshold level for at least one class. Here, dys denotes the source training feature distribution. dyt denotes the target real feature distribution. The x denotes the feature distribution divergence function, which we will look at shortly, and d theta denotes the divergence threshold. These features show the feature distribution change of 2 classes, that is class 1 and class 2, where the blue points denotes features of class 1 and the green points denotes the features of class 2. Because of the feature distribution change caused by dataset shift, the mismatch between the model's current decision boundary and the target decision boundary causes the model to make incorrect classification. Here, the feature distribution divergence is measured by the exponential of the summation of the KL divergence between the source training feature distribution and the target real feature distribution. The next thing to be determined is how to perform adaptation when the model adapts to the new dataset. In overview, the model is adapted by updating only the weight parameters at the last layer, similar to the regular transfer learning. However, for each example, we apply the loss importance to the loss at the x, which works as a dynamic learning rate, which maximizes the retraining effect of adaptation by computing the proportion of the target probability of input x to the source probability. Also, the gradient computation of weight parameters are obtained without backpropagation, which enables efficient weight parameter update by reutilizing the feature vector and the model's final probability output. Let's take a look at it in more detail. First, in order to apply the loss importance to the loss of each example, we compute the loss importance at x for example x by dividing the target real probability of input example x with the source training probability of x. The computation of loss importance at x is performed efficiently by only considering the probability of x in the same predicted class. It improves the computation overhead of loss importance by the factor of the number of total classes. Next, the weight update through gradient descent is performed without backpropagation. Instead, the gradients are computed by reutilizing the outputs of the feed-forward execution of the model. So here, at x is loss importance weight of input example x. And P of y given x is the final prediction probability of the model given example x, which can be obtained by feed-forward execution of the model with input example x. And f of x is the feature vector of the input example x at the penultimate layer of the model, which can be also obtained by the feed-forward execution of the model. The last thing to be determined is about how to learn, which decides which examples to learn in the wild for dataset adaptation. Given a stream of online examples coming to the system, we select examples to learn among them, which are expected to increase the prediction accuracy, and the model is updated with them. Specifically, we consider the uncertainty and diversity when selecting examples, which can be provided from the gradient norm of each input example without using labels. The selected examples to be learned constitute a mini-batch retraining set M for adaptation. And then the labels of those selected examples are acquired based on the active learning to perform the model adaptation through supervised learning. The first criterion for example selection is the uncertainty that estimates how much the current model is not certain about for prediction. It is based on the assumption that the model is uncertain about an example if knowing the label induces a large gradient of the loss with respect to the weight parameters, which causes a large update to the model. The uncertainty is measured by the gradient norm of each example, which requires the ground truth labels of the example. However, since it is hard to know the labels of all examples coming to the system in the wild, we compute the loss gradient as if the model's current prediction on the example is the true label. When computing the gradient norm, we can also reutilize the outputs of the feed-forward execution, that is, model's final probability P of y given x and feature vector f of x in the same way when we update the weight parameters as shown in the equation. The second criterion for example selection is the diversity with which a retraining batch for model adaptation M is composed to include diverse input examples, which results in having different output classes that the model is expected to update for. Among the selected examples based on the uncertainty criterion, a subset of examples having the largest gradient norm for each predicted class is chosen as the final retraining batch M as shown in the equation. And finally, the ground truth labels of retraining batch M are acquired, and then the model is retrained with M for adaptation. Let me show the implementation and evaluation results. We implement a microcontroller-based IoT device that performs the proposed on-device dataset adaptation. We use three widely used datasets, that is MNIST, GTSRB, German Traffic Sign Recognition Benchmark, and CIFA-10 for evaluation. Three types of dataset shifts are applied to the datasets to evaluate the proposed method. That is, a random noise shift that adds Gaussian noise to data, and a rotation shift that rotates the image data 90 degrees, and a permutation shift that rearranges data with a particular sequence different from the original one. These figures show the end-to-end adaptation process where examples of different datasets come to the system, which causes a dataset shift. They show how inference accuracy changes over the data examples by the proposed dataset adaptation. When the data is shifted, which is marked with circles, the inference accuracy drops and stays the same until the adaptation is initiated. However, once the shift is detected, which is marked with other circles, the deep model is adapted to the new data and recover the inference accuracy with examples of the new dataset. Thank you.